characteristics that we can convert quantitatively into information on what kind of materials make up the surface. That's something that's going to take us longer than the 2 weeks we've had since Flyby, but it's a wonderful data set that's going to power some very interesting interpretations of what makes Mercury's surface, how that surface relates to the atmosphere, part of which is generated from surface materials, and how both the atmosphere and the surface interact with the magnetosphere and the magnetosphere with the solar wind. Extremely dynamic planet, one where all components are strongly interacting, and one where we're going to have to watch it for some time before we can say we fully understand. The story continues with our measurements of altimeter heights as we flew over Mercury, and I would like to turn to Maria to discuss those results.
Okay, well, thank you very much, Sean. I am proud, thrilled, and delighted to be able to report the first results from the Mercury Laser Altimeter, which is a device that was designed and built at NASA's Goddard Space Flight Center. So we turned the instrument on about a minute before closest approach, and it continued to range for about 10 minutes after closest approach until the spacecraft was at an altitude of about 1,800 kilometers from the planet, which exceed its design limitation. In the first profile there, you can see in the upper left a schematic of the instrument, and you can see the profile itself. The profile is 3,200 kilometers long. It is mostly along the equator, and it actually goes about 20% around the equator of the planet. If you look at it, you can see a wide variety of craters and basins that will be interesting to look at in the future. The dynamic range of the topography is about 5 kilometers that you can see there. Also, if you look very closely, the upper left-hand part of the profile, which is about 15 degrees longitude, is about 850 meters higher than the rightmost part of the profile, which is at about 90 degrees longitude. And so there's a 0.1 degree average tilt of Mercury that appears to be a fundamental feature of the planet. And of course, we'll have to get altimetry around the rest of the equatorial region to see if that holds up, but it does look like a fundamental aspect of the shape of Mercury. In the next slide, what I'm going to show you is a close-up from the center part of the profile, and I think that this demonstrates pretty clearly just how well the instrument did in following and tracking rough topography. And as you can see, we barely lost a shot there. The instrument ranged at 8 hertz. The shots that you see there, they're 15-meter in diameter shots, spaced about 850 meters across, and you see here 2 adjacent depressions. By correlating them with an Arecibo radar image, you can see that the profile crossed 2 craters. And the crater on the left is has a diameter of a little bit more than 100 kilometers, about 107 kilometers. And the crater on the right has a diameter of about 122 kilometers. These are lower limits because we didn't profile straight through the center of the crater. And I should say here that we're using a radar, an Arecibo radar image, because during the time when the spacecraft was close enough to Mercury in order to do the ranging, the planet was in the dark, and this is also an area that wasn't imaged by Mariner 10. So this is why we're using radar. Now, if you look at those 2 basins, the one on the left there is about the same size as the Tycho crater on the moon, and Tycho is the largest young crater on the surface of the moon. But the interesting thing about the Mercury crater is that it's about half the depth of Tycho. And so it's indicating to us that craters on Mercury, or at least the ones we sampled, appear shallower than similar-sized craters on the moon. But of course, we'll have to collect a lot more data to see how that holds up. I think this just shows that in the future, when we get visual imagery along with the altimetry, as well as spectral information and other observations, that we'll be able to do geological interpretations of these structures, And also, we'll be able to do comparisons of the shapes and depths of features, various structures on the surface, and compare those to other features on the terrestrial planets where we've already collected altimetry. Now I'm going to turn this over to Bob, who's going to tell us about impact craters.
Thanks very much, Maria. Yeah, before I talk about the impact craters, I'd just like to mention something. As you can imagine, I was very excited about this mission, and particularly on the eve of the encounter, I couldn't sleep at all. I was like a kid on Christmas Eve. But unlike that kid on Christmas Eve, I'd waited 30 years for this. So I was extra excited. And it didn't disappoint me at all, because what I saw was astounding to me, because I was thinking in my mind, well, I would see, the surface like Mariner 10 saw it, but other areas. Well, I was astounded at the quality of these images. And it dawned on me after looking at these that this is a whole new planet we're looking at. In fact, when I got home, I looked at a basin called Tolstoy on Mariner 10 images, and we knew of this irregular feature in there, and we didn't know if it was volcanic or some collapse. And by God, it looks exactly like a volcanic feature we saw in the Caloris Basin. So I'm anxious to go back and look at this thing with messenger eyes. What this means is, of course, to me, this is a whole new exploration. Every part of the planet, seen or unseen, is new, is going to be new. There's no question about it, and I'm very excited about that. Now, as far as the craters, I look at craters and study them and for what they tell us about the history of the solar system and the history of the planet that has been impacted. And on the image you're going to see next is one of the Caloris Basin as observed from MESSENGER, and there are two circles on there. The yellow one is the diameter estimated from Mariner 10 images. On the right-hand side, that is a Mariner 10 mosaic, as a matter of fact. And the reason it's smaller than the blue one, which is what we measured from MESSENGER, is that we really didn't see the half of the basin. We only saw about maybe a third of the basin or so, and from that underestimated the size. So the size from Mariner 10 was estimated to be 1,300 kilometers, and in fact it's 1,550 kilometers. So it's much bigger. Now, that's one thing. The other thing is we've done crater counts within the basin itself. We now have a large enough area where the statistics are meaningful, and the crater size distribution indicate that this formed near the end of heavy bombardment, not at the end. The period of late heavy bombardment is a time in solar system history where the impact rate was much higher than it is today. And so we can estimate we know when that ended on the moon, and we can estimate when that occurred on Mercury too. And it looks like the Caloris Basin formed by a large impact between about 3.8 and 3.9 billion years ago. The other thing we learned from studying Caloris cratering record, when we started counting the craters, we noticed that just visually